Spinning metal spherical shell. A conducting spherical shell with radius capital R equals 10 cm spins about a vertical axis twice every second in the presence of a constant magnetic field B with magnitude 1 Tesla that points downward. So here is the spherical shell. It rotates with a frequency 2 Hz and there is a magnetic field 1 Tesla that's pointing downward. Two conducting rods supported by a frame contact the sphere with conducting brushes and extend away from the sphere radially. So here are the conducting rods. One rod extends from the top of the sphere and the other forms a phi equals 60-degree angle with the vertical as shown in the figure. The outer ends of the rods are connected to each other by a conducting wire that includes a 10 ohm resistor. So here we have a conducting path because it's a metal spherical shell. Part A. Construct a Cartesian coordinate system with the origin at the center of the sphere, the z-axis pointing upward and the y-axis pointing rightward, so that both rods lie in the yz plane. What is the velocity of a point on the sphere in the yz plane at angle theta measured from the positive z-axis? So here is the yz plane, and we have the rod that is vertical, and then we have another rod that makes an angle theta with respect to the vertical axis. And if you look at the sense of rotation of the spherical shell, you can see that here we have a tangential velocity pointing into the page. So this is into the page, the direction of our tangential velocity. So what happens as a result is that this point will be performing uniform circular motion on the circular path as this whole spherical shell rotates about its vertical axis, central axis. So we can see that the radius of that circular motion r will be equal to capital R multiplied with sine theta. So the projection onto the z-axis is capital R cosine theta. Projection onto y-axis is capital R sine theta. And I notice that this velocity vector is in minus I hat direction. Okay, now if it's performing uniform circular motion, because there is a constant angular speed for this shell, V is equal to omega times R, and here I can note that this is uniform circular motion, and therefore I notice that V should be written as omega times capital R sine theta. Now the frequency is given to us as 2 Hz, so it makes 2 rotations every second. And omega, the angular speed, is 2 pi times the frequency f. So we find that V is equal to 2 pi f capital R sine theta. That's the speed. Now if we calculate this, V is equal to 2 pi 2 Hertz. The radius is 10 centimeters, 10 times 10 to minus 2, and then we have sine theta. So this gives us V is equal to 1.26 sine theta. So we find that the velocity, the tangential velocity vector, V is equal to minus 1.26 sine theta I hat. It's in minus I hat direction, and it's in meters per second. So we have found the tangential velocity of a point on the sphere in the YZ plane at an angle theta measured from the positive z-axis. Part B, what is the vector product V cross B? Okay, now we have a magnetic field B which is in minus k hat direction, and V cross B then will be equal to minus 1.26 sine theta I hat cross with minus B in k hat direction. The minus signs will disappear, and I'm left with I hat cross k hat. So if I look at I hat cross j hat, that's k hat. J hat cross k hat, that's I hat. These are cyclic permutations. So k hat cross I hat is j hat, but I hat cross k hat is minus j hat. So that's the positive direction. Clockwise is the positive direction. Counterclockwise, we obtain minus j hat. So I hat cross k hat is minus j hat, and the magnitude of the magnetic field is 1.0 Tesla. So we find that the cross product, vector cross product, V cross B, is minus 1.26 sine theta j hat in Tesla meters per second. And you can also see this I hat cross k hat is minus j hat using the right hand rule. So if I have four fingers of my right hand pointing in I hat direction, which is this direction coming out of the page, I hat, and then I curl them towards the z-axis, positive z-axis, k hat, my thumb points in minus j hat direction. Also the right hand rule gives me the same answer. Okay, let's move on to part C. What is the line element dl along the shortest path on the sphere from the upper rod to the angled rod at angle theta? So the upper rod, angled rod at angle theta, we want to find the shortest line element dl for this shortest path. And you can see that since this is r, capital R, and if I have a small variation of angle theta, d theta, this dl has magnitude capital R d theta. So this should be magnitude-wise capital R d theta. Now, this makes an angle theta with the vertical axis. So if you extend this radial vector out and look at the angle with the vertical axis, that should be theta. So this is the same thing here. Now, if I complete this to 90 degrees, this is 90 minus theta. And since dl is a tangential vector, so this makes an angle of 90 degrees with the radial axis. So if this is 90 minus theta, this is theta. Now you can see that dl vector makes an angle of theta with the y-axis, and therefore its projection onto the y-axis will be dl cosine theta. Its projection onto z-axis will be minus dl sine theta, because you can see the projection is in minus k hat direction. So we can write dl vector is equal to capital R cosine theta d theta j hat, and minus capital R sine theta d theta k hat. This is our dl vector. Now, Capital R is 0.1 meters, so we can write this as 0.1 cosine theta j hat minus sine theta k hat d theta in meters. So that's the line element that's along the shortest path that connects the angled rod to the upper rod, as asked in part C. Okay, so we will continue with this. So in part A, we constructed a Cartesian coordinate system and we found the velocity vector of a point on the sphere as it performs this uniform circular motion on this circular path. And we notice that the radius of that circle is capital R sine theta, with omega, the angular speed, being the same. V is equal to omega R, and so the direction of the velocity vector is in minus I hat direction. So we have capital R sine theta, omega in minus I hat direction, and omega is 2 pi times the frequency, and the frequency was given to us as 2 hertz in the problem. So we find minus 1.26 sine theta I hat. The magnetic field is pointing in minus k hat direction. The part B asks us the cross product V cross B. So we take the cross product of this vector with 1 Tesla in minus k hat direction. So 1 times 1.26 sine theta minus I hat cross with minus k hat gives us I hat cross k hat, which is minus j hat, following this cyclic permutations. So it's 1 minus 1.26 sine theta j hat. In part C, we want to find the line element dl along the shortest path on the sphere from the upper rod to the angled rod at angle theta. So if this angled rod is at angle theta, this is the upper rod. The shortest path, on the shortest path that connects these two, we are on the spherical shell. So this makes a small angle d theta here. Capital R d theta is the magnitude. And actually you can see that if you take square root of capital R square cosine square d theta square plus capital R square sine square d theta square, cosine square plus sine square is 1, it is indeed capital R d theta. The projection onto the y-axis is capital R d theta cosine theta, onto z-axis is minus capital R d theta sine theta because of this minus k hat vector here, unit vector in the minus z direction. And we found this angle by following the geometry here. So if you look at this radial axis, it makes an angle theta with the vertical here. If I complete this, if I go to the horizontal axis, the angle with respect to the horizontal axis is 90 minus theta. So that's the angle here, 90 minus theta. But since dl is a tangential vector, it has to make an angle of 90 degrees with the vertical axis here. So this is, if this is 90 minus theta, this angle is theta. So we have dl cos theta and minus dl sine theta as the components. So since capital R is 0.1 meters, we find this final answer for the line element.